This program was produced by Blue Ridge Public Television and made possible by a grant from the National Educational Telecommunications Association's Education Production Fund and by the McLaughlin Foundation of Bristol, Virginia.
My name is Ben Bazak, a math teacher at Patrick Henry High School in Roanoke, Virginia. In 2003, I traveled with my friend and fellow math teacher, Tim McConchie, and our families to Greece, Italy, and Egypt to walk in the footsteps of the great mathematicians in ancient history. Why? Because I believe we can learn a lot from history, things that can still be useful today. So what can we learn from a Greek mathematician? Let's say you're trying out to be the kicker for your school's football team. The coach says that if you can make a field goal from 35 yards, he'll make a spot for you on the team. After a little practice, you know you can do it. But when the time comes, something doesn't seem quite right. Hey, isn't that crossbar a little higher than 10 feet? Use the knowledge of an ancient Greek mathematician to prove your point. We'll show you how in just a minute, using only the sun, a shadow, and a length of string, just like the Greeks did it. Over 2,500 years ago, a Greek mathematician named Thales of Miletus attempted to measure the most famous great height of his time, the Great Pyramid of Khufu at Giza. According to the historian Plutarch, Thales was able to measure the pyramid without any trouble or instrument, much to the amazement of his Egyptian hosts. The Egyptian pyramids were tombs that were built to serve the pharaohs on their passage into the afterlife. According to their religion, these kings would then become gods and be able to help the Egyptians on their path to the afterlife as well. With such a belief system in place, the Egyptians worked during the flood-prone, non-farming season to build the pyramids. The first tombs were simple mounds of earth, but they evolved over time into rectangular-shaped, gently sloping burial homes called mastabas. About 4,700 years ago, an architect named Imhotep designed what is probably the first vertical pyramid by stacking 6 mastabas atop each other. While not technically a pyramid with a square base and triangular sides, it has withstood the ravages of time and still stands, one of the oldest man-made structures in existence. The Egyptians continued to perfect the design of the pyramid for the next 700 years. 87 known pyramids can still be found along the Nile. Their crowning achievement is the Great Pyramid at Giza, built for King Khufu around 2600 BC. The Great Pyramid is a testament to both logistics and precise mathematical engineering. The builders fed and housed tens of thousands of workers during the Nile's flooding season and employed about 4,000 skilled year-round workers as well. Managing this in a small area such as the Giza Plateau is truly a wonder of the ancient world. The pyramid was constructed using over 2 million limestone blocks, weighing about 5,000 pounds each. It is believed that the blocks were dragged from nearby quarries up a system of ramps. Originally, there were triangular-shaped capping stones at each step to give the pyramid a smooth appearance. The whole project was completed in about 20 years using only simple tools and mathematics. The math behind the Great Pyramid has fascinated researchers for years. One theory notes that the pyramid's height is equal to the radius of a circle with a circumference equal to the perimeter of its base. Sound familiar? This would mean that the Egyptians had a fairly accurate approximation for the number pi. Another theory recognizes that the ratio of a side of the base to the height is a close approximation of the golden mean, which was used extensively by the ancient Greek builders some 2,000 years later. Finally, there is the slope theory, proposing that the Egyptian architects were trying to achieve constantly sloping sides that formed a preferred angle of elevation, perhaps found through experimentation, of about 52 degrees. Mathematical historians say that all three of these theories are believed possible, partly based on a 4,000-year-old manuscript called the Rhine Papyrus, a collection of problems that were solved dating some 700 years after the pyramids were built. So why did Thales travel to Egypt? He arrived on the world scene around 600 BC, well after the demise of the pharaohs. He was a mathematician and astronomer at a time when these fields were defined by rules of thumb, things believed to be true, but not proven. He introduced the concept of skepticism. In essence, he asked, can we prove the things that we have always held to be true? He proved, for instance, that any angle inscribed inside a semicircle is a right angle. Perhaps his greatest achievement was bringing the vast knowledge of astronomy and geometry of the Egyptians and others back to Greece, where it was used in ways that still impact mathematics, science, and architecture today. Thales was a traveler and is thought to be one of the first Greeks to visit Egypt. He amazed the Egyptian leaders and demonstrated his mathematical abilities by accurately measuring the then 2,000-year-old Great Pyramid of Giza. The Egyptians thought that the calculations for doing so would be too difficult, but Thales succeeded using only shadows and similar triangles. Like Thales, our traveling party went to Cairo to prove that these calculations can still be done at the Great Pyramid. Cairo is a city of over 20 million people, and it combines the ancient and the modern to form an urban collage of fantastic proportions. Over the past century, Cairo has crept up to and around the Giza Plain, site of the Great Pyramid. This created some interesting obstacles for us as we attempted to measure the height of the pyramid. We had to face the fact that the pyramid is missing its top. It's about 10 meters shorter than it was in Thales' time, and we were using a length of string to determine the midpoint of a side, not the most precise method. With the help of our guide, Muhammad, we performed our experiment at 9:30 a.m. on June 21st, the summer solstice, when we knew that the shadow would be perpendicular to the pyramid. Dodging tourists, cars, and camels, and under the watchful eyes of the local police, we laid out our pre-measured string to determine the approximate midpoint of the pyramid's southern side. At exactly 9:30, we marked the length of the pyramid's shadow and the shadow length of a 1.7-meter rod. As we had hoped, our calculations led us to a result that agreed with those of our old friend Thales. We found the height of the Great Pyramid to be approximately 153 meters. In fact, it stands at about 147 meters. Not bad for the equipment we used and the speed in which we had to do our measurements. Thales knew a few things that made his and our calculations possible. Let's examine our method. To start, we have to know about similar triangles. Two triangles are called similar if the three pairs of corresponding angles have equal measurement. Thales knew that the lengths of corresponding sides of similar triangles are in proportion. For example, here the ratio of the measurements of sides AB to BC is the same as the ratio of the measurements of sides DE to EF. Let's go back to our football example. When the sunlight hits the goalposts, it casts a shadow from the crossbar, 14 feet long. If we hold a 6-foot-long metal rod straight up next to the goalposts, we get a second shadow that is 8 feet long. The goalposts, our rod, and their shadows have formed two similar right triangles. Do you see the corresponding pairs of equal angles? We'd like to find the height of the crossbar. So let's set up an equation that we can solve using ratios that we know must be equal. Now let's solve. Multiply both sides by 14 and then simplify your answer. Hey, that goalpost was 6 inches too high. Remember, with a little sunshine, a length of string, a rod, and your knowledge of mathematics, you can measure the height of just about anything, just like Thales of Miletus did over 25 centuries ago.